Hello, science class. Today I'm going to be talking about acceleration, and we're going to start with 1.5, but I'm also hoping to get into 1.6, 1.7 of our textbooks. This is all dealing with acceleration and problems related to acceleration. So if you remember, it is non-uniform motion because this is changes in velocity over a given time. And so you're not always going the same speed. And so it's important to know when you're dealing with acceleration problems, you're going to be using these new formulas coming up when you're dealing with acceleration because it's non-uniform motion. Also remember we talked about all the signs and positives and negatives. Well, we're also going to be talking about positive acceleration, and I'm going to use a lot of examples of driving because that might be something we're starting to do or we have a little bit of experience with. And it's probably the easiest way to relate to people right now with acceleration. And so you can think of it as when you speed up, this is going in the positive direction. That's positive acceleration. You're going faster. When you're slowing down, that's going in the negative direction. And so negative acceleration means something slowing down in the positive direction, or it can also be speeding up in the negative direction. And so we also have to make sure we're not forgetting about directions too, but we won't have too many complicated questions like that. Here's our base formula, and hopefully we're familiar with it. There's nothing too much of a change from Science 10, except we're going to expand on it, and we're going to be dealing more with problems of not just having 0 as an initial or 0 as a final, but we're going to have speed changes, like you're driving and you need to accelerate to a higher speed. And we're figuring out these changes in velocity from two different initial and final velocities, or we have a time period where we need to figure it out. So we're going to expand on our Science 10 formula. So here you can see the formula, and we're going to start tweaking it too, because we're going to expand on some variables where maybe we don't know all the information, and how do we actually need to figure it out. So this is the formula we're going to be working with a lot, and then we're expanding on it now. So let's start by looking at the graphs of acceleration, because we just finished graphing our velocity and looking at position time graphs. But when we look at this position time graph, we can see that it is non-uniform motion. It has a slight curve. It's not a straight line. And so if we were to figure it out, at each point, the velocity is going to be different and it's not going to be uniform. So when we look at this, we have to make sure, one, we're highlighted on, okay, I know it's a position graph over time, and I know by this shape is it's curved, going up as I can follow it as much as I can. So this is non-uniform motion, so we should be thinking acceleration. So if I was to take each one of those little points and calculate the velocity at those points, and then I redid it, so I did a bunch of calculations, and it's like, okay, at time point 0.2 seconds, what is the speed or the velocity going? And I plot it. You can see by taking this information, now we kind of have a line of best fit that goes right down the middle between all these points, kind of from start to finish. And we can see now it's a nice straight line, meaning we have constant acceleration, which is what we were looking for. And so now on the sides, you can see we have velocity over here over the same kind of time spans. And so now we've figured out we have acceleration. Now that we have this straight line, we are finally able to do calculations, and we are actually able to calculate the slope. So now we can finally go velocity over time, and now our formula will actually work. Before, using that curved, we'd have to use a lot more complex math to figure out the area under that curve. So we see here, we have to determine the acceleration. So we're going to choose 2 points on the graph, and we're going to use our formula for this acceleration. So I chose these two. They were closest to some kind of two vertices, and I could use them to best estimate my points. And so that first point at the bottom had two perfect ones, and it kind of crossed right on the squares, and I grabbed that one. The second one was pretty close to being on the line, and I grabbed it. It doesn't have to be the two endpoints, because that endpoint one could have worked right over here too. However, it's a little bit far off, so I just grabbed one in the middle to kind of say you don't always have to grab the two endpoints. Because it's a straight line, we have constant acceleration. And so this graph shows uniform acceleration. Okay, and we can see this by that straight line. So when I figure it out, I want to write out my points, and you see my x's and my y points. Now, what is the actual acceleration? So pause here and try to figure it out. Hopefully, as we are able to actually figure it out, we can put it into our formula, and we're actually able to solve. And so we have x's and y's, or our y is our velocity. And so we can also sub that in. This was our y, this was our x. Hopefully I didn't need to review that. And we're just using this as our slope formula or our velocity over time formula. And we should have gotten 7 centimeters per second squared. So here's another type of problem. Are we actually able to figure it out? Please use that same formula. We have two different speeds. We have a time frame. What was the magnitude and direction of the acceleration? Pause and please try it out. Hopefully you got this answer. And you'll notice my units. So that was the big thing. We have seconds and kilometers per hour. Okay, so hopefully we can see it. Or maybe you saw it's 4.44 kilometers per hour every second, and we're going that east. So depending how you wanted to figure it out, I would always suggest convert to the same units. And for me, converting kilometers per hour, and I'm only going for 4 seconds, so I don't want some very, very small kilometer after and in hours. No, stick with my times, keep them in seconds, and go to the meters per second. But on the same hand, if you know, okay, 20 kilometers per hour, or you're changing in 20 kilometers and you go 4.5, okay, it's 4.44 kilometers per hour every second. I like this top answer. This would be the most correct and best one for you. And from there, you could always convert it. So a lot of this will be practice. So please pause the video right now and we can practice. Perfect. So now, if you can see, here's the answer for the first one. Hopefully we were able to figure that out. This is all about formula manipulation. And you'll see you have A is equal to V over T. And so what I'm going to actually do is when we manipulate it, and this is my best attempt at how to show you and remind you how to manipulate formulas, is I wrote it out here, but you'll see as I move my T over here, I cancel my T's, and then I can move my T to the other side. So what I do to one side, I must do to the other. And when I manipulate my formula, I get this new formula. So all I have to go is time times acceleration will equal my speed or my velocity. Now for the second question, hopefully we practiced it out. We have 3.67 seconds. And you'll see right here, I'm just going to retake this formula from above because I already manipulated to my linear equation. It's all nice and straight in the line. I'm not dividing. I don't have square roots or anything. And so I just carried that one down to make it a little bit easier, or I'm going to use these same steps and I'm going to do this. Instead, now I need to isolate time. So I'm going to get my A over. So I divide by A. And so what actually happens, my A's cancel. And so now time is equal to velocity over acceleration. And so I take my velocity, I divide it by 3, and I get 3.67 seconds. So I just wanted to come back to here, negative acceleration, because this is important when we talk also with things falling down and when we drop things from a height, depending whatever it might be. Here's an example of you drop something from a building and it accelerates at 9.81 seconds. Calculate the object's velocity after 1.75 seconds. And so it's like, okay, the initial speed is 0. What is my final? And we can kind of know that. So I'm going to be using that same formula right here. Velocity is equal to time times acceleration. Please figure it out. Hopefully, remember I just talked about negative acceleration. We have negative 17.2 meters per second. Remember, a lot of this unit requires you to be practicing different questions in different situations and seeing what formula and how to use these formulas in different ways. So please take time to practice, work on page 5 of your workbooks, pause it here, and then once you get through that workbook, page 5, pick up the video again. Perfect. Thanks for coming back to the video. Please practice some more problems. Here's some extra ones. This is from your textbook. Please practice these extra ones too. Like I said, lots of practice in this unit, please. Now we're going to expand on our acceleration, and we're going to start figuring out things like our displacement and how far do we go, maybe while accelerating or maybe while decelerating. And so when we do this in traffic, think of when you have to merge into traffic. You're already maybe going 60 kilometers an hour. You need to accelerate up to 100 kilometers an hour. How much distance do you have, or how fast do you have to accelerate to actually get up to speed? And so engineers and civil engineers that are planning out all the roads of how long of a roadway do you need to allow cars to properly accelerate? Because you don't want it too short on a road or else cars can't accelerate properly. And so it's things that they have to think about is how far do they have to build the road to allow for proper acceleration? When dealing with acceleration and having this non-uniform motion, we have two ways we're going to calculate displacement. Our first one is the simplest and easiest, and this is when we have a lot of our information. And so when we have our velocity initial and our velocity final, we're going to take the average of these two speeds and we're going to times it by time. And so just like how we saw, it was distance is equal to velocity times time. However, remember, this is during acceleration. And so we can't just take the one velocity and times it by time. We need the average of the two speeds. And so if you're going from 60 to 100 kilometers, okay, 60 plus 100, 160, divided by 2, 80. 80 would be your average speed. And then you times it by your time. This one's pretty straightforward. So like I said, this is going to be your bread and butter displacement formula to practice with. So please take time right now and practice these two questions. Here I gave the video, so take time and practice. Okay, so hopefully we are able to actually get this answer of 17.7 meters per second. And so determine the initial velocity of the ball. How do we actually do that? Well, we need to rearrange our formula. And we have all this information, but let's rearrange it. And so right away you can see I jumped and he's like, oh, what happened? Well, what is my velocity final? It doesn't tell me in the question, but it kind of does because it reaches its highest point, which means velocity final is essentially 0. And so even though it's nothing, 0 tells me something. It's different than just not knowing. 0 is a number. And so I just removed it. So it's velocity initial divided by 2 now times time. And so what I did over here is instead of timesing time, I divided by time. They cancel. And over here, I divide by time. And now we're left with my new formula. After that, I'm dividing by 2. So I go times by 2, times by 2. And now you can see how I move things over. And so now I can actually figure out my velocity initial. Wonderful. How can I verify it by using a different, what other different equations do we know? We know our acceleration formula. And with my acceleration formula, I have some of the very same information too. I have my changes in velocity over changes in time. So I should add a little delta symbol there as a change in velocity is equal to a change in time. So how does this help us then? Well, actually plug it in. My velocity final, 0. Okay, I can rearrange this one. My time final and time initial, well, my time, it was 1.8 there. And so now my acceleration which I know as negative 9.81, try to rearrange and see if you can verify your answer. All right, so here we have our second way to calculate displacement with this non-uniform motion. This one's important because what happens if you have no idea what your final velocity is? This equation will take into effect the part that you're accelerating, and all you'll need now is to plug it in, and it's a little bit more complicated because we have exponent and we're dividing, but it's nothing too complicated, and I'll show you some tricks as we practice through. So here we go. Pretty much we're plug and play because we know all the information, and some of it we're going to have to kind of just think of, what do I actually know? And so a person leaves the surface of the trampoline with an initial velocity of 11.8 meters straight up into the air. What is her displacement after 0.8 seconds? Okay, so our formula doesn't need manipulation. And when we go through it, when you look at your formula, think check mark, check mark. Acceleration? Yeah, check mark. What is our acceleration? Well, we're dealing with gravity. And so our gravity is right here. So it's 9.81 meters per second squared. Okay, and so we are dealing with gravity and we're going straight up. And so that's our acceleration. So it doesn't directly say what is our acceleration, but it is our gravity. And so as we calculate it all the way through, remember we're going up and we're bouncing up, so we're accelerating. Her displacement is 12.6 meters. Okay, pause here. Please work on now page 6 of your workbook. Take time, go through some of the practice equations. It talks about calculating displacement in non-uniform or accelerated motion and knowing how to use both formulas. I'm not going to trick you again. The textbook extra practice is right there. It helps to go through some of these practice questions, and it also helps explain some of the processes of how to rearrange formulas on some of the side notes. So this really does help. And it does take a lot of extra practice. We would have spent a lot of time in class just having work periods to practice through it. So not just learning terms and going over definitions, but it's practicing these word equations. So please, please pause right now and practice. So the last little bit of our video here is 1.7, determining stopping distance. And so now you can think of it as how far are we going as we decelerate? And we're going to start talking about, okay, when we actually see things and stop, and how far do I travel while trying to brake? The first part about this is it's going to be two things, because when we're driving, we're going to always be going at speed. Even if we are reacting, we're going to be covering some amount of ground. And so this reaction distance, and usually it's like 0.75 seconds for you to actually see the danger, and then it's like another 0.75 for you to actually react to it. And so by the time you actually visualize and process, and then actually think, I need to move my foot over to the brake, takes about 1.5 seconds for the average person to react to a situation. Another assumption of average things, so just like how we have a reaction distance, and that time it takes, we also have an average deceleration or an average braking deceleration, and we're just going to use these assumptions. Every car is different. Obviously, a semi-truck and a train would have different decelerations, but on average, we're going to use this number for our cars to decelerate at. And so this is our braking distance. Once you're going 100 kilometers on Deerfoot, well, you're still going to travel some distance as you slam on the brakes. And chances are, let's use this average number of negative 5.85 as our deceleration. Now that we have these two different distances, we're going to look at the big picture of what it would be our total stopping distance. And simply, it's the distance we go in the time we react and the distance we go when we're actually actively braking. On the next slide, we're going to have a problem, and it's pretty much this, is we have our distance that we have for our reaction distance, and then our braking distance. It doesn't look exactly like this because as you go faster and faster, it will change how fast or how long your braking distance is. But we're going to be going 110 kilometers, and we're going to figure out the area under these curves. Essentially, this will give us our displacement. So here's our practice question. We're going 110 kilometers an hour. We need to stop. What distance do we actually travel? If you want to practice, pause it now, try to get this answer. If not, let's work through it together and figure out stopping distance is made up of these two different distances. And so this is important because our reaction distance is going to be uniform motion. We're not braking yet, we're not decelerating yet, we're just traveling at a constant speed. How far did we go? Our braking distance, this is where we're actually decelerating, and we're going to have to calculate non-uniform displacement. So here, very straightforward, our reaction distance, no problem. We should have no problems figuring this out. It says velocity times time. The time I gave you was that constant. It's 1.5 seconds. It would have been a given, and I told you that in a previous slide. So when we plug it in, oh, kilometers per hour second doesn't work. So convert units right away. Choose meters per second, because meters per second, and we're going to be dealing with our accelerations. It's just much easier to go with meters per second. It's going to be your basic unit. Always try to get into those if you can. Calculate it out, very straightforward. Hold on to that number till the end when we have to add it to our braking distance. But that's incredible that by the time we just react, we've gone almost 46 meters in 1.5 seconds. And so that's an incredible distance. Wow. So think of that next time you're driving. For our braking distance, we're going to use this formula. Remember, we have non-uniform displacement, and how do we figure it out? Well, we're going to take our average velocities, just like we did before, because we're not going at a constant velocity, so we need our average velocity times time. Except, what's our time? It's not 1.5 seconds, that was our reaction distance time. Well, we can actually figure that out though. And so here, if I go back to my acceleration, it's just a change in velocity over a time. And I do know my acceleration because I told you that in the other slide was that negative 5.85 meters per second. And so our final velocity is what? That's right, it's 0. We're stopping. And so what we're left with is here, we have a negative VI divided by time. Well, let's rearrange for time. Let's swap our time, swap our acceleration. Remember, we can solve it out. And so we have negative VI over our acceleration, which is negative 5.85. And so once we get that, here I'll substitute it in. It was struggling with me with my time, so I can go 30.5 repeating negative meters per second, and it was negative 5.85 meters per second squared, and they all cancel out, it's seconds. Yeah, it was struggling with all these numbers in units and everything. Now that we've figured out this important part right here, we can take this time and use it in our non-uniform displacement formula. So what we see here is I have my velocity initial. I converted it from before. Remember, it's a repeating, so you try to keep the repeating. Plus our 0 as our final, our average, so it's about 15, divided by 2, times by the time we just figured out, and we got this distance. So our displacement is 79.798 meters. So pretty straightforward. We just have to do a little bit of formula manipulation on some and just kind of piece together the puzzle. Now that we have it, we take our two distances, our reaction distance plus our braking distance equals our stopping distance of 125.6313, or we go with our significant digits of 126 meters. Whew. So practice questions like this. These ones are the tough ones where they're multi-stepped, but we can puzzle solve and kind of figure out what do I need to do. These ones are where the practice comes in help. All of this is kind of impressive because think of it, if you started driving, they call it yellow light timing, or they call it the point of no return. And so as a young driver, you're still trying to figure out how much time do I have to get through that light by the time I see the yellow to react to brake, and then to actually brake, do I have enough distance that I should just clear the intersection, or do I have enough time to brake and stop at the proper line? And so they call this the point of no return. This is where your stopping distance, so reaction plus braking, is not enough for your whole car to end and not end up in the middle of the intersection. And so it's kind of that point where, uh-oh, I need to go through the light rather than trying to stop. And so you need to determine the maximum length of time it would take the car to clear that area with uniform motion. And so, okay, if I just stay at that speed, will I clear through before it turns red? So it's a tough thing to learn of this, uh-oh, do I stop? Do I have time to stop? Or do I just accelerate through? And that's where a lot of people will get red light tickets because they don't determine their yellow light time well enough. It's always best practice to try to brake if you have time to. So please try this one where determine the minimum length of time for a yellow light in an area where the cars are traveling at 60 kilometers per hour. And so how long would that light need to be lit? Because if it's on for 3 seconds or 4 seconds, does that give you enough time as a fair warning? If in that previous example, well, we needed a timing of to decelerate was 5.22 seconds. So what would it be at 60 kilometers per hour? Work through similar type of question. So I'm going to leave it here. I won't fool you again. I threw in the extra practice from the textbook. But please work through the workbook on pages 6 and 7. Work through those ones. And then there's extra practice in our textbook as extra practice questions. Please practice them. Okay, so we're going to have a few more notes come Tuesday because it's a long weekend. So it's going to be a lot of practice, practice, practice. Take care for now, and we'll get ready for our quiz at the end of next week. Bye.